Hi class, let's get down to business. Let's talk about actually finding solutions to first and second order linear recurrence relations. For first order linear recurrence relations, we have the following result. Proposition. For a recurrence relation of the form an is equal to s times an minus 1 plus t, where s and t are real numbers, solutions will have the form an is equal to a0 plus n times t when s is equal to 1, and an is equal to c1 times s to the n plus c2, where c1 and c2 are real numbers whenever s is not equal to 1. Here's an example in the case where s is not equal to 1. Consider the sequence 1, 5, 13, 29, 61, etc. This can be written down in terms of the recurrence relation an is equal to 2 times an minus 1 plus 3, where the initial condition a sub 0 is equal to 1. In terms of trying to find a solution, s is going to be equal to 2 and t is going to be equal to 3. So by our result, solutions will look like an is equal to c1 times 2 to the n plus c2, where c1 and c2 are real numbers. How do we find our final solution? As in, how do we figure out what c1 and c2 are? We're going to just solve our linear equations by looking at some early terms in the sequence. So, a0 is going to be c1 plus 2 to the 0 plus c2. That is going to be 1 as the first element in the sequence. a1 should be c1 2 to the 1 plus c2. This is going to be 5. All right, now let's work this out. This first equation gives us that c2 is equal to 1 minus c1. And so that tells us that 5 is equal to 2c1 plus c2, which is 1 minus c1 from the second equation. And we get 4 is equal to c1. And that gives us that c2 is equal to negative 3. Altogether, our solution is going to be an is equal to 4 times 2 to the n minus 3, also known as 2 to the n plus 2 minus 3. Okay, our proposition tells us that this is what our solution should look like. Let's just double check by induction. We have that a0 is equal to 1 and an is equal to 2 times an minus 1 plus 3. And we want to show that an is equal to 2n plus 2 minus 3 solves the recurrence relation. Our base case is the n is equal to 0 case, and we see that a sub 0, which is equal to 1, is indeed equal to 2 to the 0 plus 2 minus 3. We're going to assume the statement holds true for n is equal to k, and then do the inductive step. K plus 1 is equal to 2ak plus 3. We apply the inductive hypothesis, work out the algebra, and we get that ak plus 1 is equal to 2 to the k plus 1 plus 2 minus 3. And that proves our statement. So let's talk about second order linear homogeneous recurrence relations. Notice, say r is a real number and it happens to be a root of an equation x squared minus s1x minus s2 is equal to 0, where s1 and s2 are real numbers. Then r squared minus s1r minus s2 has to be equal to 0. Pulling terms to different sides, we get s1 times r plus s2 is equal to r squared. And then by multiplying through by r to the n minus 2, we get s1 times r to the n minus 1 plus s2 times r to the n minus 2 will be equal to r to the n. Altogether, this means when r is the root of this quadratic equation, r to the n satisfies the recurrence relation an is equal to s1 an minus 1 plus s2 an minus 2. That is, it satisfies a second order linear homogeneous recurrence relation. Let's put this together with what we learned about the vector space structure of solutions of solution spaces to these recurrence relations. Theorem. Suppose S1 and S2 are real numbers and R1 and R2 are roots of the quadratic equation x squared minus S1x minus S2 is equal to 0. If we take a look at the recurrence relation, n is equal to S1 times an minus 1 plus S2 n minus 2, where S1 and S2 of course are real numbers, then we know something about the form of the solutions. If R1 and R2 are different roots, as in they're not equal to each other, then every solution for this recurrence relation has the form n is equal to C1 R1 to the n plus C2 R2 to the n, where C1 and C2 are real numbers. If R1 is R2 and they're not equal to 0, then every solution has the form n is equal to C1 R to the n plus C2 times n times R to the n. Let's do an example. Let's check out the Fibonacci numbers. Fn is equal to Fn minus 1 plus Fn minus 2, where f sub 0 is 0 and f sub 1 is 1. In terms of using our theorem to find the solutions for this, S1 is going to be S2 is equal to 1. The associated quadratic equation is therefore going to be x squared minus x minus 1 is equal to 0. And when we solve this quadratic equation, we get that x is going to be 1 plus or minus root 5 over 2, all over 2. That means our solution is going to look like f sub n is going to be equal to c1 times the first possibility for x to the n plus c2 times the second possibility for x to the n. Now, how do we figure out what c1 and c2 are? Just like in our previous example, we would use our initial conditions to set up two equations and solve those equations for C1 and C2. Given the initial conditions, F0 is 1 and F1 is 1, we can therefore recover Binet's formula for the nth Fibonacci number, written like so. Next class, we're going to be talking about when the solutions for our recurrence relations are given by polynomials.